I neglected to start the thing recording when I started the class a while ago. So for anybody watching this on YouTube or on Canvas, you've missed 27 minutes of class. Sorry about that. I do want to work over this problem with everybody on Gauss's law, because believe it or not, once you get Gauss's law, once you get your mind wrapped around what it means and how to use it, it greatly simplifies a whole bunch of things. But just working your way through the definitions of what it is and what it means, it can be kind of confusing. So we are going to come back to it after the exam. We are going to work our way through Gauss's law and understand exactly what it means. Right now, we're just going to look at use it as an equation, as a formula. Now, the problem says that the total electric flux Anybody else feel snake bit today? The total electric flux emanating from a cubicle-shaped box is 1.85 times 10 to the 3 Newton meters squared per Coulomb. And it also tells us that each side of the box is 28 centimeters squared. Now, if we use Gauss's law, which is equation 16.9 on page 464, we find that the total flux is equal to the sum of the perpendicular E field times over each little increment of area, and that will total the enclosed charge divided by epsilon sub naught. So, now in order to use Gauss's law, you have to sum the E field, perpendicular E field, over an entire enclosed surface. In this case, a cubic-shaped box of 28 centimeters per side. And when you do this and you carry out the summation, it'll give you the total flux. In this case, we're already given the total flux. We're given this sum right there. So we don't need to do all of that. We're told that this is equal to the enclosed charge divided by epsilon sub naught. Let's look at some dimensional analysis here, because this might help you if you think about this. This might help you at least keep it sorted in your mind for the time being. What are the units of E? Newtons per Coulomb. What are the units of area? Meters squared. So the units of phi, of the flux, are Newton meters squared per Coulomb, not newtons per Coulomb. Right here. They gave us those units in the definition, in the problem, in the question. What are the units of epsilon sub naught? It is a constant, but
The C squared over Newton times meter squared, right?
it's, say again now?
C squared over Newton times meter squared.
You're going to get in trouble saying C squared in a physics class. say Coulomb squared.
Sorry.
No, that's okay. Yeah, let's go find the actual number. It's written down in
1.6022
1.6 epsilons of naught.
I believe so. That's 8.85.
Yeah, that's there's K. Yeah, here it is. That's the charge of an electron, that 1.602 times 10 to the minus 19 coulombs. Here we have it, down at the bottom, 16.2. The bottom of page 448. Epsilon sub naught is equal to 8.85 times 10 to the minus 12 coulombs squared per Newton meter squared. Now, here, let's just do some dimensional analysis here real quick. The total enclosed charge is obviously units of coulombs. And epsilon sub naught is in units of Coulomb squared divided by Newton meter squared. Well, we know that division is simply multiplication by a reciprocal, so we can redo this as coulombs times Newton meters squared per coulomb squared. Now, one of these coulombs cancels with that one, and we end up with epsilon sub naught, with Q enclosed divided by epsilon sub naught as equal to Newton meters squared per coulomb. That's what we need. Newton meters squared per coulomb is equal to Newton meters squared per coulomb. So, we're looking for Q enclosed. So I'm going to move over and start over again where it won't be quite so messy. What is the total flux? 1.85 times 10 cubed Newton meter squared per coulomb. And that's equal to Q enclosed divided by epsilon sub naught. So if we multiply both sides by epsilon sub naught, we end up with 1.85 times 10 to the 3 Newton meters squared per coulomb times 8.85 times 10 to the minus 12 What are our units? Coulomb squared per Newton meter squared. Is equal to our Q enclosed. Looking at our numbers, we have newtons canceling newtons, meter squared canceling meter squared. One of those, that coulomb canceling one of those, we end up with this number of coulombs is equal to coulombs. So our unit analysis bears it out. And for our number, we get 1.85 times 10 to the 3 multiplied by 8.85 times 10 to the negative 12. And that gives us 16 times 10 to the minus 9 coulombs. And it looks like he carried out one more decimal place than we did.
If we wrote it as like 1.64 times 10 to the negative 8, it's the same thing, so you wouldn't care, right?
Oh, yeah, no, 1.64. 1.64, no, it wouldn't be the same thing. Yeah, it would be. 1.64 times 10 to the minus 8 would be 16.4 times 10 to the minus 9. In general, if you notice, the prefixes move in groups of 3 decimal places. 10 to the minus 9 has a nice, neat little prefix. I think it's nano. Yeah, 10 to the minus 3 is milli, 10 to the minus 6 is micro, 10 to the minus 3 is nano, 10 to the minus 12 is pico, and I have to look them up beyond that. But, yeah, as long as the number's right.
And on your test, do you go by, like, say we got part of the problem right, and then we accidentally wrote a wrong number, do we still get partial credit on it?
Oh, yeah, yeah, you're going to get partial credit. Where you will lose more points. Yeah, obviously, to get the most points, you always want to show your work. You want to do the work correctly and get the right number, and that'll give you the most points. I really don't care that much if you punch in the number wrong on your calculator or make some arithmetic error, as long as you're doing the work correctly. So yeah, you're going to get credit for knowing what you were doing. Absolutely. That matters more to me than just getting the right number. I think the way I've explained it before is, you can tell me 2 plus 2 is 4 and still be wrong if you think it has anything to do with purple. So I want to know that you know why 2 plus 2 is 4. And that you can get the 4 is the right answer. But yeah.
Is the math going to be all math-based, or is it going to have some definitions?
What do you mean?
I mean, it's like we'll have the definition of an electron or something like that, or is it just going to be all math?
The definition of an electron would. Yeah, no, you're going to want to know the problems on the test are going to be very much like the problems you just did in the homework. I'm not going to throw curveballs at you. My objective is not to cost you points. My objective is for you to understand what we're doing and how we're doing it and why we're doing it. I really would love it if everybody aced the test. Especially because that makes it a whole lot easier on me when it comes grading time. But yeah, you're going to want to have some. I'm sure you're probably going to need to know the charge of an electron, and that's exactly the sort of thing that you would want written down on that standard sized index card. I have been asked, can you use both sides or just one side? You know what? You can use both sides, and if you can read it, you can write on the edges. I don't care. You can have one index card, one standard index card. Do not come in with a poster board and say it's a really big index card. Okay? I don't know what the standard size is, if it's 4 by 5 or 3 by 5, but I think you'll notice, you'll recognize a standard index card when you see it. Number 27. Love it. Man here for business. Number 27. An electron electron is released from rest in a uniform electric field and accelerates to the north at a rate of 105 meters per second squared. Find the direction and magnitude of the electric field. Okay. Now let's draw. Start by drawing our picture. Cannot stress how important it is to start by drawing a picture. Oh, and by the way, it would be a very good idea to have K and epsilon sub naught as some of the things that are written down on that index card. Okay. Electron is released from rest in a uniform electric field. So here's our electron, and it accelerates north at 105 meters per second squared. What do we know? What can we know immediately, just from the problem definition? First thing we know is that the E field, if the electron is accelerated this direction, this must be the positive source of the E field. And that tells us that the uniform electric field is pointed south. Okay. What else do we know? We know that force is mass times acceleration. We know that in the case of an electron in a uniform in any electric field, but in a uniform electric field, we know that force is equal to Q times E. Q being the charge of the electron. So we can just write this as mass times acceleration is equal to Q E. Well, we've got the direction of E, so all we really need is the magnitude of E. Right? Who knows the mass of an electron? Right off the top of your head. Anybody? That's the charge of an electron.
9.11
Mass of an electron. Sounds like something that needs to be on an index card. Right? Say that out loud again. 9.11 times 10 to the minus 31 kilograms.
How did they ever get that number?
Millikan oil drop experiment. Millikan oil drop experiment. Like an oil drop, a mist of oil with little tiny drops in between charged plates. No, that's one electron. It takes like a bajillion electrons to come up to a kilogram. Well, actually, it takes almost 10 to the 30. It takes 10 to the 30 of them to get close.
How did they ever think about doing that?
We were trying to figure out what electrons were. Still haven't really figured it out. When you get into quantum physics, you're going to find out that that electron that everybody thinks of as a little point charge, this little solid piece of 9.11 times 10 to the minus 31 kilograms of mass that is negatively charged, that circles around that proton and that hydrogen atom, that ain't what they look like. That's our analog. That's how we envision them in order to understand them. But in reality, an electron is a wave. It's wave energy. You can't add kilograms and seconds. You can only add kilograms to kilograms. What's the only thing you can add to an electron? Is a photon. And a photon is transverse electromagnetic wave. And, but we are nowhere near going into quantum physics. Okay, so everybody forget everything I just said right there. As far as we're concerned, an electron is a little bitty tiny, it's 9.11 times 10 to the minus 31 kilograms of mass with a negative charge of, what's the charge of an electron? That little piece of mass has an electric charge of minus 1.602 times 10 to the minus 19 coulombs. That is an electron. You want a definition for an electron? Write that on your index card. That's the definition of an electron, as far as this class is concerned. Something times 10 to the minus 27 kilograms. Like 1,800 times the mass of an electron. I don't remember. Oh, yeah, this is 1.602. Let me try to write that more clearly. And it's a negative 1.602 if you're talking about the charge of an electron. If you're talking about the charge of a proton, it's plus 1.602 times 10 to the minus 19 coulombs. If the charge of a proton is simply the positive of this E would be the fundamental electric charge. It's negative if it's an electron, it's positive if it's a proton. Okay, back to our problem. We now have the mass to put in here with the acceleration, and we know the charge, Q. We're ready to solve. MA equals QE. And what we're solving for is E. We know mass, we know acceleration, and we know Q. So we divide both sides by Q. And we end up with MA over Q equals the magnitude of our E field. Plug in the numbers. Everybody plug in the numbers and let's see if we all get the same thing. Okay, hold that number. I don't punch that fast. Let's see. What did you get?
5.97.
That's what I get.
Okay.
Does everybody else get 5.97 times 10 to the minus 10? Okay, before we go on from this problem, I want to do the unit analysis. What is E? Newtons per coulomb. Mass times acceleration is newtons, right? Kilograms, meters per second squared. Q is coulombs. Newtons per coulomb equals newtons per coulomb, and we're golden. 3 more minutes. Anyone have another question?
31.
31. Determine, can we do it in 3 minutes?
Yeah, we got it.
I got down to one part and I wanted to take natural log of it and some other stuff because it just looked like natural log, but then I can't do that.
Well, with the calculator we can, but I really don't think I would have assigned you a problem that you would have to work out natural logarithms on. At least not without giving you some heads up warning about it.
I got it down to this one part where KQ bracket 1 over x plus 2 squared minus 1 over x minus 2 squared bracket. And that's when I wanted to start doing the natural log there.
Nope. Yeah. Well, let's. Yeah, that sounds a whole lot more complex than this problem really is. It's actually just another. You find the E contribution of the positive particle. You find the E contribution of the negative particle. Now, in this case, I'll wipe all this out. All right. What do we have? We have a plus Q and a minus Q. 2A apart. Now, there you have a point X away from the center. Now, what does that look to you like? Express your answer in terms of Q, X, A, and K. Okay? Well, you have a minus Q here, a negative charge, and a plus charge. So we're going to look at 2 different fields. Here we have the field of Q1. We'll call it E1, and that's equal to K times Q1 divided by R squared, where R in this case is X plus A. Now we have a second contribution to the field here, that is this one. that is the same thing, almost. E2 is equal to K times Q2 divided by, and this is R1 squared. We'll call this R2 squared. But now R is not X plus A, it's X minus A. That's the total, that's the two magnitudes. But this one, Q1 and Q2, Q1 is emanating from the positive going this direction. Q2 is emanating from the negative, which means it's going in this direction. Now all you have to do is find the magnitude of those two vectors, take the vector sum. Yeah, you subtract. Yeah, you have this E plus this E. So the vector sum would be Q1, Q2. And it would be the vector from here to here, which will actually, because X minus A is shorter, is closer, this should be the larger vector. So the net on this side, if with the negative Q on this end, the net vector will be this one. Okay, now let's make sure I didn't turn those around when I wrote the problem. I put the negative closer to P and the positive farther from P, so yeah. Does everyone see how to do this one now? I think you can all put the numbers in and punch the calculators. All right. Class is over, but if you want to do another problem, if you have more questions, I'm good. I think I'm going into office hours now, so. And if you are ever looking for me during office hours and I'm not there, just look right down here. I'm not far. And yep, this is office hours, so